and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Rachel Thomas. Amid much controversy, the 2022 World Cup has begun, and the action has now moved onto the football pitches inside the many newly built stadiums in Qatar. But how are these stadiums turned from architectural sketches into real buildings? To find out, we're reaching way back into our archives to one of the first podcasts we ever recorded back in 2007. My colleague Marianne Freiberger spoke to Paul Shepherd from the University of Bath. Paul's an expert in building football stadiums such as the famous Emirates Stadium in London.
I'm talking to Paul Shepherd of the University of Bath, who until recently was working for the engineering company Bureau Happold. And he's been involved in building a lot of big structures, especially stadiums. And one of his projects was the new Arsenal Stadium in London, the Emirates Stadium. So, Paul, can you take us through what you've been doing there and the mathematics that is involved?
Yes, well, it's a huge project, as I'm sure you can imagine. And there are so many different things to take account of when you're building a stadium, but mathematics has been fundamental to most of those. The architects have a vision. They do the creative design as to what the stadium has to look like when it's finished. And it's the engineer's job to turn that vision into a reality, really. And we have to make sure it would obey the laws of physics, it would be strong enough, stable enough, able to withstand whatever might happen to it during its life. And that's whatever the weather can throw at it. But also the people are important, the interaction of the people who use it. It's a very different stadium when it's got 60,000 people in as to when it's completely empty.
So you were talking earlier in your talk, you were talking about the crowd dynamics.
Well, stadiums these days aren't just used for watching football matches. There are often other events and pop concerts, things like that. And what we have is people who go to these concerts, often quite lively, they move about, they jump up and down, especially if there's music. And so when we're building the stadiums, we have to make sure that the stadium can withstand 60,000 people jumping up and down. And with music it's especially important because everyone's in time with each other. So what we have is there's a phenomenon called resonance, and the stadium has its own natural frequency. It's like when you pluck a guitar string, it has one particular note that it likes to vibrate at. And all the stadiums, you don't tend to think of a stadium as a guitar string, but a stadium has a natural frequency at which it wants to vibrate. So we have to use mathematical models and computers to be able to predict the frequency that the stadium would vibrate at, and then we can tune that frequency by adding more structure or taking structure away to make sure that the frequency is not the same as what people are going to jump at.
So you mentioned Belgian techno earlier,
Yeah.
So how does that come in?
Well, we need to know how the stadium will respond, and we also need to know at what frequency the people will jump at. So there's been some research into different pop songs and the frequencies of different pop songs. And they showed that Belgian techno was it was the fastest type of music that's ever likely to be shown in a concert, with a frequency of about 2.8 hertz. So when we're designing the stadium, we have to make sure that the frequency of the stadium is very different from the 2.8 hertz it could be jumped on.
So what kind of frequency do you choose then?
Well, there are a number of different things coming into play, and we make sure the rule is to make it above 6 hertz, and that's been very carefully chosen to be more than double the 2.8 that the people could jump at. And once we're more than double away, we can be fairly sure that the two won't interact, and the people in the stadium will be different enough so we wouldn't get a problem.
And what kind of mathematics exactly is involved? Like, is there an equation that somebody at school might be familiar with?
It is very closely linked with the pendulum. People are probably familiar with a grandfather clock or a pendulum that has its own natural frequency. And in a pendulum, the length of the pendulum has a bearing on the frequency at which it swings. In our case, instead of the length of the pendulum, we have the stiffness of the structure and the mass of the structure. and the ratio of those two go into defining how the frequency at which it vibrates. So we can change the mass of our stadiums by adding in more material, and we can change the stiffness of the structure by adding in extra structural members, and using those two we can tune the frequency up to be above 6.
And once you've built a structure, or if you're looking at a structure that has already been built, how do you test its frequency? Apart from theoretically, but how do you actually make sure that your calculations were right and that it is the right frequency?
Well, that is an interesting one, because we have to have confidence in our mathematical equations and our models. And so we have lots of research that's been done which can go and measure something that's already been built can be measured. So they take a rotating weight and they stick it on the stadium, and it rotates and it shakes the stadium.
So you actually shake it?
So they actually shake stadiums and measure the response, and they can work out what frequency it swings at.
Now, what about the structure? Because you were talking earlier about the roofs, and especially if you're building a football stadium, you can't put any columns in the middle because the pitch is there. So obviously a lot of thought has to go into how to construct the roofs, and you were talking about this finite analysis.
Finite element analysis.
Exactly. So yeah. Can you just give us a little overview of that?
Yeah. There are different methods of working out how structures will behave, and we have to make sure that they are strong enough and stiff enough that they don't move too much. So we build 3-dimensional models in the computer, and materials behave in a quite predictable way. That is something that people do in physics class, is they look at stress and strain and Young's modulus. And so the stress and the strain are related in a very simple way. But the problem with the stadium is the shape is very complicated, and you have lots of long bits of material, long span trusses which bridge right across the pitch so that you don't need a column in the middle. So we use finite element analysis, which divides the structure up into lots of little tiny squares, and we know fairly well how each little square or rectangle will behave in this fairly simple way. And so by splitting the entire complex shape up into small rectangles, applying the maths to the small rectangle, and then putting the results all back together again, we can get a very good idea of how complex shapes behave, and by applying the very simple equation to them.
And another consideration that you have when you build these huge buildings is safety, for example, fire, and maybe the crowd behavior in panic situations. So what do you do about fire and smoke? How do you model that?
Yeah, a lot of the work of engineers is about making sure the structures can withstand extreme events. So it's not enough to say that it'll be happy most days in the year, but we have to think what possible things could happen to this during its lifetime of 50, 100 years. So things like earthquakes or explosions or fires, we hope that they'll never happen, but we have to make sure that if they do happen, the structure is safe and the people inside them are safe. So we use, again, mathematical modelling techniques. We can model smoke using computational fluid dynamics, which we can make sure that the smoke has a path to exit the structure, that the people won't be caught in too much smoke. The fires themselves have to be analysed. We can adapt the finite element analysis techniques to take into account of a fire, because a fire affects the way the material behaves, and there is generally thermal expansion when things get hot. So we can add those into our models as extra factors, and then we can do highly complex analysis on the same structures. So we've got confidence that in a fire or in a smoke situation, the structure would still be able to withstand the extra loads.
You also said that you tested your predictions about fire by setting a building alight.
Yeah, that's right. Many years ago, there was a research project which constructed a full-size 8-storey building and set fire.
Was it a real building,
A real building, full scale, and it was set fire to. But before they set fire to it, they put lots of measurement devices in to measure the change in stresses, the temperatures, and the displacements, the movements of the building. And so that, again, was a way of getting confidence in our mathematical models. The thing about a mathematical model is it's relatively cheap to model 10 different cases. You can pretend there's a fire in this corner or the other corner. And when you're doing a full-scale test, it's quite expensive, so you can only do a limited number of tests. And then you use those tests to prove your mathematical model's accurate, and that gives you confidence to then apply that mathematical model on other things. So we really called the fire brigade before we set fire to a building and then set fire to it.
Okay, another thing that you mentioned was parametric modeling, or parametric design, I suppose it's called. Could you explain what that is?
Yeah, it's a new technique that's just starting to be used in the building industry, and it allows you to describe the shape of a structure in the computer using equations rather than by the historical methods where people just drew them by hand. We're actually fitting equations to these complex shapes, and we're using rules to relate them together. So instead of saying a beam goes from A to B, you can say a beam goes from the top of this column to the top of another column. The advantage of that is that then if things change, if the column position moves, the rule is still applicable, so the computer can recalculate based on we've moved this column, but the beam still goes from the top of it to the top of the other one. So it really allows us to build a model using equations to define the shape and relationships between those parts of the building. And we can make changes very quickly with the input, and the computer then processes the rules in exactly the same way, and we can get very different buildings out the other side.
So this allows you to build certain variables into your design that you can change. Like, for example, you mentioned the height of columns. So you could build that into your model and say, well, I might want to change that along the line. So what kind of factors would you typically, if you build your stadium, which kind of factors would you want to keep variable?
Yeah, that is the question. It gives another sense of creativity in a way. It really makes you think, what are we trying to achieve? What's going to be important to us? Where does our flexibility lie?
And you mentioned, I think it was in the Emirates Stadium, or maybe the other stadiums as well, I suppose. What about the sight line? And didn't you say that from the beginning, the view from every seat was taken into account in the kind of parametric model?
Yeah, we've always used sight lines as one of the things we take into account when we're designing. It's very important to sit in your seat and be able to see what's going on in the pitch clearly. So we've always taken it into account. But this method of using rules to define the geometry allows you to choose rules that have some kind of physical representation. So we're not randomly choosing a number to describe how high the building is, but we can make it a sensible choice. So we've done work where we've built in sightline information into the rules that drive the shape of the building, and that way you can be sure when you're playing around with these numbers and changing the values of parameters that as the computer then reconfigures to give you a new stadium, the new stadium will still be very good with sightlines, because that was one of the rules you built in.
So are you a football fan?
More so than I used to be.
So you feel safe in stadiums on the whole then?
Yeah, absolutely. I think I've seen more pop concerts in stadiums than football matches, but these days they're used for so many different varied uses that the designers have to take these things into account, otherwise you've just got something that's only good for watching football, and it's just not a waste of a stadium, really.
Okay, well, excellent. Thank you very much.
You're welcome.
That was Paul Shepherd talking to my colleague Marion Freiberger about the maths of football stadium back in 2007. If you've enjoyed this podcast, you might enjoy another recent episode called How the Velodrome Found Its Form, which we released on this channel back in August. And you can find out much more about the maths of sport and the maths of engineering and architecture at plus.maths.org. Thanks for listening, and bye-bye for now.